Production.
In Greek mythology, Icarus met a tragic end when he dared to fly close to the sun.
3, 2, 1, 0, and ignition and liftoff.
Today, scientists are daring to soar even higher, this time on sturdy metal wings, to probe the secrets of the sun. On February 11, 2010, a new solar journey kicked off aboard NASA's Solar Dynamics Observatory, or SDO. The 7,000-pound spacecraft will orbit 22,000 miles from Earth to record changes on the sun as they happen, nearly every second of every day for 5 years. It's a veritable reality show of our brilliant star with nothing left out, yielding 50 times more data than any mission in NASA's history.
The Solar Dynamics Observatory will give us a constant view of the sun. We refer to it as the sun all of the time.
The resolution that we're going to have on the sun is just incredible. 16 million pixels. That's 10 times the resolution of a high-definition television.
NASA has sent other spacecraft to study the sun, namely SOHO, SDO's older brother. Operating since 1995, SOHO captures only a third of the sun in high resolution for only 2 months a year. SDO blazes ahead of SOHO with its continuous, vastly superior imaging of our stormy cosmic neighbor 93 million miles away.
The sun is very much larger than the Earth, and its atmosphere extends out through the entire solar system, and we call that the heliosphere. We as a planet live in the heliosphere, and we're subject to its weather.
It may sound like science fiction, but this space weather originating on the sun is very real and very fierce. Take, for example, a coronal mass ejection, an eruption of 1 billion tons of charged particles from the sun's outer atmosphere that can bombard Earth in a few days. Then there are solar flares, monstrous explosions which erupt from the sun with the force of 20 billion nuclear bombs, unleashing gamma rays, X-rays, and energized particles that can get to Earth in minutes. Luckily, Earth's outer atmosphere acts as a magnetic shield that blocks some of the radiation from space weather. But if an event is large enough and aimed at Earth, it can actually move this magnetic shield, inducing currents along power lines and blowing out transformers. In 1989, a massive solar storm left millions without power in Quebec, Canada. Despite our planet's protective umbrella, space weather poses an ever-increasing threat because of our dependence on technology, which has brought us closer, but has also brought the sun closer to us.
We have many satellites now for all sorts of purposes, for weather, for communications. Any one of them can be damaged by one of these solar weather events. And each time one of them is, it's somewhere between $300 million and $1 billion that's lost.
What SDO is going to do is enable us to be able to predict when these features are going to explode, when the big energy is going to happen, well enough that we can actually take action.
Space weather for 24 hours has been high.
But space weather is tough to predict because what's driving it is the sun's ever-changing magnetic fields.
What we really want to understand about the sun is where the magnetic fields are formed, how they get to the surface so that we can make a forecast of how much magnetic activity there's going to be.
Sunspots are the fingerprints of the invisible magnetic fields that can point to bad space weather ahead.
So these magnetic fields come through the surface of the sun as sunspots, and there's a positive and negative polarity, and they're connected. Material collects on those field lines. The material that's collected on there is fairly stable, but what happens when another sunspot comes up? You'll have a short circuit, and that short circuit will cause the magnetic field to change or to collapse. It releases a lot of energy.
This awesome energy is the space weather that hits Earth.
We're kind of like detectives. What we're looking for is a life story of these magnetic fields as they emerge as sunspots as they heat the atmosphere above, as they release the space weather. How do you tell that whole story?
While watching a softly spilling sunset, it's easy to forget the violence this storied star in the sky is capable of. But there are times when its temper cools.
The sun has a cycle. It lasts about 11 years, but not exactly 11 years. It can be as long as 14, 15 years, as short as 8 or 9. For a while, there are more sunspots, and then for a while, there aren't any sunspots. For a while, the sun is magnetically active, and for a while, the sun is magnetically quiet.
When the sun's magnetic activity spikes, so does its space weather. But no matter how active or quiet the sun is, it needs fuel.
The sun is under a lot of pressure because of the gravity pushing down. So in the center, there's fusion going on. That's hydrogen atoms, hydrogen nuclei, protons, crashing into each other and fusing into helium.
And in that process, a certain amount of mass disappears. It gets turned into energy. About 4 million tons gets turned into energy every single second.
There's enough hydrogen to power the only star in our solar system for 4 billion more years. Plenty of time to discover the missing pieces that explain its volatile activity. Armed with a suite of instruments, SDO delivers the optical supremacy we need to see every layer of the visible and invisible sun. Untitled works at Lockheed Martin's Solar and Astrophysics Laboratory in Palo Alto, California. He designed the high-tech eyes that SDO uses to stare at the sun.
The Atmospheric Imaging Assembly Telescope is just one of the 2 instrument systems we've built here in this laboratory. The other is the Helioseismic and Magnetic Imager that we built in partnership with Stanford University.
These aren't your typical surveillance cameras.
This telescope makes images in the extreme ultraviolet, regions of the spectrum that we can't see. The extreme ultraviolet is essential for us to understand the hot outer atmosphere of the sun. The HMI instrument will allow us to see magnetic field below the surface before it emerges as a sunspot.
Then, when an event happens, scientists can go back and see what the conditions were like above, below, and on the sun. Welcome to a state-of-the-art solar theater with special screens built to keep up with the solar action captured by SDO.
This screen is not a screen that you can buy at your local TV store. It's the equivalent of 4 HD TV screens all playing at once.
And the scientists aren't merely watching the sun in cinematic splendor. They're also using SDO's cameras to map and measure it.
We fill the camera up with the image of the sun, 16 million pixels. So that means each pixel is about 250 miles across. So by having all of these pixels, we can track what's happening at each location.
But to track the activity across the shifting landscape, you have to not only look, but listen to the sun.
The sun is like a big drum. It's pulsating all the time. There's a boiling going on. And that causes these low-frequency sound waves. Now, with the sun, you can't hear the sounds directly because there's nothing between the sun and the earth. So what you can see is you can see the vibrations. Just like at the drum store, when the drum was hit, it made other things vibrate. These sound waves are inside the sun and they bounce off the surface. It's just like the sounds from the drum bounce off the window in the front. And when they come to the surface, we get a glimpse of where we've been. Helioseismology is the study of the inside of the sun. That's where the real action is.
Helioseismology. It's a mouthful. But this powerful technique allows scientists to look beneath the sun's surface for sunspots before they pop up and erupt with space weather.
What we're looking for in helioseismology is where the wave originally started. And then sometime later we see it at a different part of the image. It's traveled inside the sun and come back to the surface. And we can correlate those two and we can tell that it's the same wave. By looking at each pair of points all over the surface of the sun, We can tell if there's a magnetic field there to make the wave travel a little bit faster.
And now with SDO, these sonic mapping and tracking efforts are about to get a boost.
And we're going to be able to resolve beneath the surface of the sun much more clearly where the magnetic field is. The reason this is going to be better is because SDO has much sharper vision. It's like having